Okay, thanks a lot. So my name is Richard Gast. I'm a PhD student at the Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig. And today I'm going to talk about neural synchronization and bursting dynamics in spiking neural networks with short-term adaptation. First, let me thank the organizers of this whole event and of the symposium for having me as a speaker. The work that I'm going to present today I have performed together with Thomas Knösche and Helmut Schmidt from the Brain Networks group in Leipzig. You can find a link to our group website and our Twitter account down here, together with a link to the publication that covers most of the results that I'm going to talk about today and has been recently published in Neural Computation. Okay, so this is the outline that I put together. First, I'll give you a short introduction into some aspects of short-term adaptation. Then we'll have a look at the network model that I considered, the effects, the results of the bifurcation analysis that I performed on the model, and then we'll summarize these things. All right, so let's start with short-term adaptation. It comes in different flavors. It has been identified in different neuron types at different brain sites. The two types of short-term adaptation we'll consider today are synaptic depression and spike frequency adaptation. The former is thought of as a multiplicative downscaling of postsynaptic potentials. You can see this in the top left corner here for a synapse in the basal ganglia, where you can also see that dopamine can actually modulate the strength of the short-term adaptation. And the other one, the other mechanism is spike frequency adaptation, which is thought of as an additive balancing current triggered by the spiking activity of a neuron itself and leading to an increase in the interspike intervals of that neuron for a short amount of time. And such short-term adaptation mechanisms have been linked to the maintenance of certain interesting dynamic operating regimes of the brain or of neural networks in general. And in the computational neuroscience literature, specifically in reservoir computing, for example, they have been suggested to have a positive impact on computational capacities of spiking neural networks and their dynamic regimes. For example, here on the right column, we can see a randomly connected recurrent neural network, and you see two autocorrelation matrices and two connectivity matrices for all the network units in that model. And they are shown for two different time steps throughout a sequential training procedure. And you can see that the autocorrelation matrix adapts together with the structural connectivity matrix and forms a picture that is representative of the generation of synfire chains. So this is an interesting dynamic regime. And in this paper, they showed that this only appeared in their model when they had certain short-term adaptation mechanisms in place. So in general, we asked ourselves in very simple, recurrent, excitatory populations, if we add short-term adaptation, what kind of macroscopic dynamic regimes can we get from that? And what kind of microscopic computational capacities do these dynamic regimes allow for? And this is still ongoing work, so we don't have finished all of this yet, but I'll mostly show you the network models that we developed and the macroscopic dynamic regimes that we identified. So let's have a look at the network model that we considered. So the basic neuron model that we looked at is the quadratic integrated fire neuron. So here you can see the evolution equations for a recurrently coupled population of quadratic integrated fire neurons. And the evolution equation of the single cell is governed by an intrinsic excitability parameter, eta I, some extrinsic input, I of t, and then the single cell is coupled to the mean field of the whole population. So the average firing rate, which is here abbreviated as S. And if we consider J to be 0, so the recurrent coupling strength and the extrinsic input I, then the dynamic regime of the single cell is purely governed by the eta I. If it's negative, then we have two equilibria in the system, one stable node, representative of a resting state, and one saddle, representative of a firing threshold. If we increase eta I towards 0, those two states approach each other and eventually annihilate each other. And for positive eta I, we have a periodic firing of the single cell with the frequency of the firing depending on the magnitude of the eta I. So this is the behavior of the single cell without any adaptation. And now we added different adaptation mechanisms to that, to these network equations, namely synaptic depression and spike frequency adaptation. So synaptic depression we implemented, or in the model as a postsynaptic depression mechanism where the mean field input of the network to the cell is scaled by a neuron-specific depression parameter AI or adaptation parameter AI, making that input neuron-specific. And the adaptation dynamics are governed by a convolution of the mean field input of the network with an adaptation kernel G, which we chose to be the alpha kernel. So we have both the rise and the decay dynamics of the adaptation variable. For spike frequency adaptation, we simply added a balancing current to the membrane potential evolution equation of the single cell AI, which is not driven by the mean field, but instead by the instantaneous firing rate of that neuron, here labeled Ri. And the adaptation dynamics, however, are also governed by a convolution with an alpha kernel, which can also be expressed as two coupled first order differential equations, AI and BI over here. I just simply didn't write it down on both sides, but the adaptation dynamics are the same. Just the input to the adaptation variable is different and where it enters into the evolution equation of the membrane potential. So what we wanted to do now in order to later on compare macroscopic and microscopic networks and their dynamic regimes is derive low dimensional representations for those networks. The general idea is depicted over here. So if you consider a coupled network of quadratic integrated fire neurons, we would like to derive dynamic equations that directly describe the evolution of two macroscopic state variables, the average firing rate and the average membrane potential, here depicted in yellow. And they should be equivalent to calculating the average over all network units of the single cell quantities, the single cell membrane potential traces and the single cell spike traces. Here depicted the average calculations in black. And this has been performed for that particular network without adaptation by Montbriot and colleagues in 2015. They published this in Physical Review X. So they considered an all-to-all coupled network in the thermodynamic limit. And they considered a Lorentzian distribution over the background excitabilities in the network. So we have a heterogeneous spiking neural network. And then they used a Lorentzian ansatz, meaning that they assumed the membrane potentials inside the population to be distributed according to a Lorentzian as well. This choice is, however, independent of the distribution that you choose over the background excitabilities. And they set up then a continuity equation for the evolution of this membrane potential distribution in time, shown down here. And if you plug in the equation of this membrane potential evolution probability distribution into this equation, you can solve for its statistics, x being the half width at half maximum and y being the average of, or the mean of the Lorentzian distribution. And those two quantities can be directly related to the average membrane potential and the average firing rate inside the population. And for this particular choice of the distribution over the etas, you can solve for those two variables, and then you end up with two coupled first order differential equations. And we could follow a very similar path for our work. For the synaptic depression, we could actually follow exactly those steps, because our adaptation variable is driven by the mean field, by the mean firing rate. For the spike frequency adaptation case was slightly different. There we had to additionally assume that the adaptation evolution is slow in comparison to the evolution of the membrane potential inside our network. If you want to check out the specifics, you can look at the publication. But those were the two low dimensional network representations that we ended up with and that we analyzed later on. I will now present you the results of this analysis. Only for the synaptic depression case, though, they were very similar between the two cases. So if you want to also see the results of the bifurcation analysis for the spike frequency adaptation model, then you can also check out the publication again. It's free content online on the Neuron Computation website, so don't have any license problems or anything. Okay, so let's have a look at the parameter dependencies of that model here. So all the parameter continuations and bifurcation analysis that we performed with the continuation software Auto. And here in the bifurcation diagrams in the top row, we depicted the location of all equilibria in our system with respect to the state variable R for different values of the background excitability parameter eta bar, representing the average of the background excitability distribution in our microscopic model. And you can see that for an adaptation strength alpha equals 0, so no adaptation, the model is governed by two different stable states, the one being a stable node, representative of a low activity state, and the other one being a stable focus, representative of a high activity state. And there exists a bistable regime where both of these can coexist and are separated by a cell focus, as shown here in the dotted line. And if we now increase the adaptation strength, there's a bounded range in alpha, where additionally we run into a Hopf bifurcation, actually two Hopf bifurcations for these parameter continuations in eta bar. And investigating the properties of the limit cycle emerging from this Hopf bifurcation, we find that it's an unstable limit cycle colliding late. So this is actually a subcritical Hopf bifurcation, and it collides with a stable limit cycle via a fold of limit cycle bifurcation later on. And we depicted here in the subfigure B the minimum and the maximum of the limit cycle of the stable limit cycle in green. So you can see that there's a regime where the stable limit cycle is the only stable attractor in our system. And you can see in the subplots C and D that this stable limit cycle is characterized by highly synchronized firing activity indicative or representative of bursting dynamics in our model. And we can find that both in the mean field model shown in yellow and in the microscopic spiking neural network shown in black with the spike traces below. And we also find a bistable regime where we can have both the bursting limit cycle and the stable focus coexisting, and we can switch between them via transient inputs, as shown here in subfigure E. And here you can see a 3D projection of our 4D state space for this bistable regime, where we initialized our system at different points around the unstable limit cycle and then integrated the model in time. And you can see the trajectories that either converge to the stable focus in purple or to the stable limit cycle depicted here in green. So what we've learned by now is that different forms of short-term adaptation, because we can find the same results for spike frequency adaptation as well, actually lead to the emergence of highly synchronized bursting regimes in our QIF population, and also allow for a bistable regime where you can quickly switch between this highly synchronized bursting regime and a steady state regime. So the next thing that we asked ourselves is how adaptation timescales can actually affect this behavior. Specifically, we were interested in the rise time of our adaptation variable, since in the computational literature, lots of different short-term adaptation mechanisms, specifically spike frequency adaptation, is often modeled as an instantaneous variable. So the rise dynamics are considered to be fast in comparison to the membrane potential dynamics. So we can do this same thing in our model by replacing the convolution with the alpha kernel as the adaptation dynamics with a convolution with a mono exponential kernel. This effectively reduces the dimensionality of our model from a 4-dimensional model to a 3-dimensional model, the mean field model. But except for that, basically the model stays the same. The adaptation variables still enter in the same place in the equations and everything. And if we do that and we look in this 3-dimensional model with the mono exponential adaptation again, for our bursting limit cycle and perform the same parameter continuations, we find that again, we run into two Hopf bifurcations. However, those Hopf bifurcations are now supercritical. And first, near the Hopf bifurcation, the second one here on the right-hand side, a small amplitude high frequency limit cycle exists, which is not representative of bursting behavior at all. As you can see here in those relatively uniform oscillations, and here on the right-hand side, you can see the state space representation. However, it then undergoes a cascade of period doubling bifurcations, here shown as those black pentagons, which then describe a transition to this large amplitude, low frequency bursting behavior that we've seen in our other model. And along this transition, along this cascade of period doubling bifurcations, we also find chaotic behavior in our model. So this indicates to us that the rise time of the adaptation variable can directly describe the transition between a chaotic regime in our model and a regime of highly synchronized firing activity. And we actually were able to confirm this via direct parameter continuation by using a bi-exponential adaptation model, and then continuing the rise time of the adaptation towards 0. And then we also run into the same period doubling cascade. And this is of course interesting since, as we heard earlier, cortical dynamics are considered to operate close to a chaotic regimes by some people, and that different pathological cases come with these highly synchronized bursting activities, such as epileptic seizures, for example. And we can do this here in a very simple setup with a purely excitatory recurrent neural network with a simple adaptation variable. And we've also know that these adaptation variables can be modulated, for example, by dopamine or something like this. So a change in the adaptation timescales is not that biologically unrealistic. So in order to now use those different macroscopic states that we identified and basically inform microscopic networks with them in order to see what they implicate for their computational capacities, we have to make one additional thing sure. Namely, during the mean field derivations, we always assumed all coupled networks in the thermodynamic limit, so with infinite amounts of neurons. And this is, of course, we cannot simulate infinite amounts of neurons. And all coupling is also something that is definitely not beneficial for the computational capacities of a recurrently coupled neural population. As we know from the reservoir computing literature, we would like to have some form of sparseness in the coupling of our network. And so what we did in the next step is we violated some of the assumptions that we made throughout our mean field derivation and set up microscopic networks of different sizes and only realized a certain percentage of the connections randomly inside the network between 1 and 100%. And we initialized the model in a dynamic regime where the bursting limit cycle was the only stable attractor, and compared the bursting frequency and the bursting amplitude that we got from numerical simulations in time with what we predicted and simulated also from our mean field model. And you can see color-coded here the difference in the bursting frequency and the difference in the bursting amplitude between our microscopic models and the mean field model for the different network sizes and the different coupling densities. And you can see some exemplary time traces here on the right-hand side. And what we observe is that while the network size always has a positive effect on the match between our microscopic model and our mean field model, when we increase it, of course, the story is slightly different and more nonlinear for the coupling density, where for small networks, actually intermediate coupling probabilities gave us an optimal match with the mean field model. For example, here for a microscopic network with 1,000 units, we can see that the bursting frequency and amplitude pretty much matches perfectly with the mean field model, while for the all-to-all coupling, so here time series 3, has a way lower frequency. So this is nice in a way for us, since it means that we can set up a relatively small network, so with a few thousand units and sparse coupling between them, and still be able to inform them via our mean field model and still have some insurance that we can still find the stable states that we predict from our mean field model in those sparsely coupled small networks. And this is what we've done so far. We want to basically do the same thing now for the chaotic regime as well, and see under which conditions we find those in such small sparsely coupled networks as well. So here is our conclusion. And then we would like to set up microscopic networks with in those dynamic macroscopic regimes that we identified via our bifurcation analysis, and identify and examine how those different dynamic regimes affect the computational capacity. So for example, the ability to discriminate between different inputs and things like that in those dynamic regimes, and close to the phase transitions between those dynamic regimes. So that's it from my side. Thanks for your attention, and now I'm ready to receive your questions if there are any.
Thank you very much, Richard. Yes, there is indeed one question from the panelists, which unfortunately do not show in the Q&A. How does the transition look between the dynamics of the STA between the exponential dynamics, or the first order dynamics, and the second order dynamics, where you have this different...
Okay, so how does the transition look? So what I've already did so far, and what I haven't shown yet, is that I initialize, so that I use a model with a bi-exponential description of the adaptation dynamics, which gives you independent control over the rise and the decay time constants in the model. But if you set them to the same value, this model is equivalent to the alpha kernel. And so I use this description for the adaptation, and I initialize the model here at this orange marker. So at a point where I know that there's chaotic dynamics in the mono exponential, with the mono exponential adaptation. But then I set up the model such that it's equivalent to the alpha kernel. And for this particular value of the eta bar, in the alpha kernel model, we just have stable bursting, right? And then I continue the time constant of the rise time towards 0. And for this 1D parameter continuation, when I'm sitting on the limit cycle, so I'm continuing the periodic solution, I'm running again into a period doubling cascade, which is very similar to the one shown over here. And I'm ending up also with the chaotic dynamics of the rise time of the adaptation, of the bi-exponential adaptation, is small enough. And small enough is a bit below the time constant of our membrane potential.
Yeah, I think that already asks to some extent 2 more questions. There's one question from Dmitry Todorov. Do transitions between chaotic bursting equilibrium regimes depend on the time constant as well?
Yeah, that would be answered by that, right? It does. Yeah. So we can directly, by reducing the rise time in a model with bi-exponential adaptation, move the model from a bursting dynamic regime to a chaotic regime.
Okay, and one question from Joel Tabak. The timescale of synaptic depression determines the slow burst timescale. Yeah, what determines the timescale of the fast oscillations during a burst?
This is the timescale of the focus in the QIF network, right? So as you can see here, for example, in this figure, we have these 2 fold bifurcations of our steady state in the model. So, and this you find also if you have no adaptation. This is a simple effect, these just describe the dynamics of the QIF network. And the upper branch is a focus. And this focus describes the fast activity in the bursting. So basically the bursting is the transition between the low activity node and the high activity focus.